Thermodynamics, very easy chapter, and you will get many statement type results from this chapter which you can use for short answer questions in school examination as well as for NEET and JEE. Look, how do we handle this chapter? First thing in thermodynamics is first law of thermodynamics. Let's talk about first law of thermodynamics. Now, what is first law of thermodynamics? Let's write down the statement first and then you will understand what does it mean. dq is equal to du plus dw. You may also find it written in this form: delta q delta u plus delta w. Whatever version you prefer, you can use it. We'll take this one: dq, du, dw. What's the meaning of all these things? First, let's introduce dq, du, and dw, and then you will understand meaning of this first law. Write down few things. Let's first talk about dq. Write down with dq. dq is heat supplied to the system. dq is heat supplied to the system. Now, what is system? You have a cylinder. There is a piston which can move up and down, and there is a gas inside. These are gas molecules. That's the system for us, these gas molecules. This gas inside the cylinder is the system which I will be using for the equation. When I say dq is heat supplied to the system, that means heat supplied to the gas. Now, let's complete the sentence. dq is heat supplied to the system if heat is received by the system, then dq is taken positive. If heat is received by the system, then dq is taken positive. And if system rejects the heat, if heat is coming out, if system rejects the heat, then dq is taken negative. Let's say you supplied 100 joules of energy to the system, 100 joules. As you supply 100 joules, your dq will be plus 100. Now, in a different process, what happened? 80 joule energy came out from the system. Now, how does it come out? You will see that later. Suppose 80 joule energy came out. If it came out, then you will say that dq is minus of 80. Heat supplied and received by the system is taken positive. Heat rejected by the system is always taken negative. Now, next thing, du. What is du? du is change in internal energy of the system. du is change in internal energy of the system. U for internal energy, D for change. du is change in internal energy of the system. Internal energy of a system depends on its temperature. Internal energy of the system depends on its temperature. We'll develop a function for that later. But right now, just write down the statement. Internal energy of the system depends on its temperature. If temperature increases, if temperature increases, then du is positive, and if temperature decreases, then du is negative. If temperature increases, du is positive. If temperature decreases, du is negative. Now, next is dW. dW is work done by the system. dW is work done by the system. That means by the gas, not on the system. Remember, what is dW? Work done by the system. Work done by the system is positive if volume of the system increases. Work done by the system is positive if volume of the system increases. And when volume decreases, work done by the system is negative. Work done by the system is negative. Now let's first understand the equation. dq equals to du plus dw. Suppose you supply 100 joules of energy to the system. Now, when you supply 100 joules of the energy, out of this 100 joules, 20 joules was used in increasing temperature or internal energy of the system. This 20 joules is used by the system for increasing its own internal energy. And then remaining 80 joules was used as a work. Now, what is work? Suppose, just take this system. This is a piston. If you connect the piston to a disc like this, this is the axis of the rotation of the disc, and that's where you have connected the piston, not exactly at the center of the center. Now, if I provide 100 joules of energy, then out of this 100, 20 joule was kept by the system in the form of its internal energy, increment in the internal energy, and then this piston started moving up. And as this piston starts moving up, this wheel or disc rotates with some angular velocity omega. I'm just giving you a simple example. So this omega means this disc has a kinetic energy of half I omega square. Now what is that which provided this half I omega square kinetic energy to this disc, the system? That half I omega square in this basic example is work done by the system. So now you can see that this equation is therefore a very basic statement. You are simply saying that somebody gave you 100 rupees, and out of this 100 you kept 20 with you in your pocket and you transferred 80 to someone else, and that means what? 100 is 20 plus 80. Now, we'll first develop this dW. We'll understand work done by the system, and when I told you that if volume increases, work is positive, if volume decreases, work is negative, you will understand these things with the help of this diagram. So, that's your piston. Volume of the gas is V, and pressure right now is P. Cross-sectional area of the piston, is A. If cross-sectional area is A, that's your piston, and all the gases inside, these gas molecules, they are pushing on the piston, and therefore they are creating what? A force. Because of that force, because of this force, this piston moves from this position to this position. That's the new position. Now when it moves from this position to this position, let's say displacement is dx. That's your small displacement. What is this? Force. Force generated by the gas molecules. As they hit and collide with the piston, they produce what? Force. This force produces what? A displacement of dx. If you have force, if you have displacement, then you know about work. What is work? Work is force multiplied by the displacement dx. And since in this figure force and displacement are in the same direction, you will write what? Cos 0. That's how you write work. Now, for gases and all, instead of using force, we prefer what? Pressure. And you know what pressure is? Pressure is force divided by area. So what is the pressure? What is the pressure acting on the piston? On this movable piston, what is the pressure? Force divided by cross-sectional area of the piston, A, which gives us force as pressure multiplied by area multiplied by dx. Now look at this part, A dx. What is A dx? What is A? Cross-sectional area of the piston. What is dx? The movement which you have produced in the piston. That means this much extra volume, not the distance. Distance wise it is what? Dx. Look here. If piston moves from this position to this position, this much distance is what? Dx, but the entire volume which is now present here, the entire volume of this region, that entire volume is not V, because V is what? Initial volume, and therefore you say that this additional volume which you have created is what? dV. From this position to this position, displacement is dx, and extra volume created is what? dV. I hope you can see that this dV is nothing but A multiplied by dx. What is volume? Base area multiplied by height. Base area is A and the height is what? Dx. That gives us A dx as dV. This is your dW. For any type of thermodynamic process, any type of, what do I mean by type? Isothermal, isochoric, isobaric, any kind of thermodynamic process, your dW from now onwards will be P multiplied by dV for any type of process, and therefore always write down like this inside a boundary. It's a result for you, small result. Now let's understand the statement which we had with this dW. I told you that if volume increases, then work done is positive, and if volume decreases, then work done is what? Negative. Look, first of all, from this, what is dV? dV is always V final minus V initial. When you write dV type of thing, it's always what? V final minus V initial. So, if you say that volume is increasing, if volume is increasing, then this dV is positive. If dV is positive, that means your dW is also what? Positive. And if volume decreases, that means final volume is less than the initial. That will give you what? dV as negative. If dV is negative, your dW will be what? Negative. And therefore, when you say that volume increases, work done is positive. If volume decreases, work done by the system, by the gas is what? Negative. Now, you can also understand this positive and negative with the help of this diagram. If I ask you that this piston is going up, which we have used in this equation. If it goes up, then force and displacement both are in the same direction, and therefore we are using cos 0. Now suppose the second situation where this piston is coming down. Now if I ask you, if this piston is coming down, then what is the direction of this force? And many times people say that since piston is coming down, force is also downwards. No. What is system? System is what? These gas molecules. These gas molecules, they are always moving randomly. And as they move, they go and hit the piston. If you collide with this piston, then that force in all situations will be like this, acting towards the piston. Because this force is nothing but kind of normal reaction force. You go and hit the wall. When you hit the wall, that is what? Normal reaction force, and you know that normal reaction force, it always acts towards the body. That body is the piston. So, if this piston goes up or it comes down, whatever be the situation, this force is always going to act towards the piston. Now, in a situation where your piston is coming down, if it comes down dx, I told you that force is still up. For this situation, if you write work, then that work will be force into dx into cos of angle between force and displacement. Force and displacement, that angle is what? Pi, 180. And what is cos pi? -1. And therefore, this is coming what? Negative. Now, from now on, you don't have to worry about whether the piston is going up or going down. What is the angle 0? What is the angle 0 or 180? From now on, you will simply look at this figure, PdV. If volume is increasing, work is positive. If volume is decreasing, work is negative. I have explained how come it's positive and negative. Now, first thing, note down this much, and then we'll find work for different type of processes. Note down this much. Let's see work for the very first process, which is isochoric. Isochoric process. Now, first of all, what is isochoric? Isochoric means constant volume. If I ask you what is work done in a process where volume is not changing, then I hope you can easily answer that work done should be 0. That's why I said that in this chapter you will get so many one-line statements like this. For an isochoric process, a process in which volume is not changing, a process for which dV is what? 0. If volume is not changing, that means V final and V initial, they both are same, and therefore your dV is what? 0. Or you can say that if volume is not changing, that means that piston is not moving. If piston is not going up or down, that means its displacement is what? 0. If there is no displacement, work is what? 0. That's your first process done. Work done for an isochoric process is always what? 0. Now, write down the next one. Find out work done. Find out work done for an isobaric process. Work done for an isobaric process if pressure is P. What is isobaric? Isobaric means pressure is what? Kept constant. If pressure is P and volume changes from V initial to V final, or temperature changes from T initial to T final. Throughout the process, your P pressure is what? Constant. That's your isobaric process. Isobaric. For isochoric, your volume was constant. Now, let's say there are n number of moles. For n number of moles at constant pressure P, volume changes from V initial to V final. Or you say that temperature changes from T initial to T final. Then find out work done by the system in an isobaric process. Pause the video, try to find the answer, and then come back and see the solution. Look here, for any type of process, work is this, dW equals to PdV. But since we need W, we will be using what? Integration. P dV. Starting from V initial to V final. We need W. What is W? Integration of dW. This is your dW. What is work? Integration of dW, which is what? P dV. Now what is P? P is constant. If P is constant, you know that this constant will simply come out. Inside, it's what? dV. So what is integration of dW? W. So what is integration of dV? V. Integration of dV is coming V, and then the limits V initial to V final. You know that? How to put limits? P upper limit, V final, lower limit, V initial. That's your work done by an isobaric process. It's a result. Note down this thing inside a boundary like this. They are all one-line statements. For isochoric, work is 0. Result. For isobaric, work is P times V final minus V initial in terms of volume. But we also need work in terms of what? Temperature. So if I ask you what is work in terms of temperature, then you will use this. What is P into V? N R T. So when V is initial, T is initial. You cannot change P. Isobaric pressure is what? Constant. Next time, this is P, V final, which is what? N, R. This is your T initial. make it T final now. So when you increase your volume from V initial to V final, temperature is increasing from T initial to T final, increasing or changing, whatever it happens. But your pressure will remain what? Constant. And this equation, if I ask you, what is PV final minus PV initial? Subtract. What is this then? Take an R common. If you take an R common, then this is becoming N R T final minus T initial. This is your work in terms of temperature for an isobaric process. In terms of volume, it is what? P times V final minus V initial. In terms of temperature, it is what? NR T final minus T initial. Note down this much. Now let's see work for an isothermal process. Isothermal process. Isothermal means what? Temperature is constant. The entire process you keep your temperature what? Constant, and you are changing volume from V initial to V final, or pressure is being changed from P initial to P final. And as usual, we have got n number of moles. Write down the statement. Find out work done by the system in an isothermal process where temperature throughout is T, capital T, and volume changes from V initial to V final, and pressure changes from P initial to P final. Again, pause the video, use that equation, find out work, and then come back and see how do we handle it. We need W, which is what? Integration of dW. Same steps, which is what? Integration of pdV. But this time round, you cannot take this P out because P is also changing. And you cannot integrate it at this stage, pdV. So, how do you integrate it? We'll be using PV equals to nRT. That gives us P as nRT divided by V, which becomes W. What is P? nRT divided by V multiplied by dV. Now all the constant terms, take them out. N is a constant, number of moles. R is a constant, gas constant. T is kept constant because process is what? Isothermal. So this is N R T, and what is inside? Inside you've got dV upon V with limits from V initial to V final. Now everybody knows how to integrate dV upon V. What is integration of dx upon x? Log x. And therefore integration of dV upon V, you should remember this. Integration of dx upon x is log x base E, which is in short called ln x. When you write ln, remember base is what? E. So for us, W is n r t. Just like dx upon x, we have got dv upon v, and therefore its integration is ln v with limits from v initial to v final. How do you put limits? N r t, upper limit log v final minus log v initial. Remember, at times people do what? They simply write ln v final minus v initial. No, we use limits with the whole function. Upper limit ln v final minus lower limit ln v initial. Now, this is what? Log a minus log b. What is log a minus log b? Log a upon b. That gives us n r t log of v final upon v initial. Work done in an isothermal process, again inside the boundary, an important result, nRT log v final upon v initial. Now if I ask you that, write down this whole thing again in terms of P initial and P final, then you would do what? What is P V? It is N R T. When pressure is P initial, volume is V initial, and this side is what? N R T, which is also what? P final V final. So initially P initial, V initial is what? nRT. And finally, P final, V final is what? nRT. And therefore, you get from this V final upon V initial, V final upon V initial as P initial upon P final. Put it in this equation and it becomes N R T log of this V final upon V initial is P initial divided by P final. P initial divided by P final. In terms of V volume, it's final upon initial. In terms of P, it's P initial upon P final. Remember this nRT log V final upon V initial. Mostly we'll be using this, and then it's a very easy task to convert this format into this format. Also inside the boundary. That's how you calculate work for an isothermal process. Around this much. The fourth process is an adiabatic process. What is an adiabatic process? A process in which no heat transfer takes place of the system with the surrounding. Suppose you have a piston which is equivalent to a thermos flask. In a thermos flask, the intention is that no heat can come outside. So a system like that, in which you cannot exchange heat from the surrounding, is called an adiabatic process. For an adiabatic process, I will give you this information that P V gamma is constant. How do we arrive at this? We'll see it later. But as of now, remember that for an adiabatic process, equation is PV gamma as what? Constant. Just like an isothermal process, PV is what? Constant. For an adiabatic, PV gamma is constant. What is gamma? We'll see that later. For now, remember that whatever gamma is, it is always greater than 1. For now, you just need to remember these two things for an adiabatic process. First, the name. It means no heat transfer. Then, relationship between pressure and volume is PV gamma constant. This gamma is called adiabatic gas constant. What does it mean? We'll see later. And is always greater than 1. So, pressure, volume, temperature. Nothing is same. Everything is changing. Pressure changes from P initial to P final. Volume changes from V initial to V final, and temperature changes from T initial to T final for n number of moles. And we need to find work done in an adiabatic process. So you will start from what? This equation. dW equals to PdV. Write down this. W is what? Integration of dW. What is that? Integration of P dV. Everything is same so far. No change. Then again, what is P? This W is now P. You can always convert P as nRT upon V. But then there is no advantage this time. If somebody tries this thing, just like the isothermal part, if you write P as N R T upon V into dV. So far there is no problem. The point is that you can only take N out and R out. This T and V, they both are not constant. Everything is changing. And therefore, from this step, there is no point in moving like this. I have given you what this PV gamma is constant. What is this constant? We have no idea. This constant is what? C. If this constant is C, once I say we have no idea, what is the constant? This constant is what? Pressure multiplied by gamma power over V. That is this constant. So, what is P? P is some constant divided by V to the power gamma. What is P? C upon V gamma into dV. Lower limit, upper limit. At this stage, pause the video and integrate the whole function. Ultimately, get your answer in terms of P, V, and T. And then come back and see how do I handle it. This C is a constant, take it out. If C is out, then this is V to the power minus gamma into dV. Everybody knows how to integrate x to the power n. X to the power n, its integration is V to the power minus gamma plus 1 divided by minus gamma plus 1. That's the integration. X to the power n, n plus 1 upon n plus 1. This whole thing, you need to use your limits from V initial to V final. Then work is coming, W is coming, C, take it out, divided by, look at the denominator, this is now 1 minus gamma. Let's write down the denominator as 1 minus gamma, and then upper limit is V final 1 minus gamma minus, this is V final 1 minus gamma minus lower limit V initial 1 minus gamma. Not a very difficult task. Simple integration and then use what? Limits. That's your work. But let's write the value of C. What is C? C is what? PV gamma. So what is C? Look here. C is P initial V initial gamma. At the same time, this C is what? P final V final to the power gamma. Your pressure is changing, volume is changing, but this product with gamma is not. Same happens finally. So let's multiply this C inside. When you multiply C inside, first, this is what V final. With V final, you will take the value of C as P final V final to the power gamma. C multiplied inside, it is P final V final gamma. And already you have what? V final to the power 1 minus gamma minus. When you multiply C with V initial, you will take the value of C as P initial V initial gamma. And therefore, now your C is P initial V initial gamma multiplied by V initial to the power of 1 minus gamma. Whole thing divided by 1 minus gamma. Hopefully you can see the answer. What is the answer now? This is V final to the power gamma. This is V final to the power 1 minus gamma. When you multiply these things, you add the powers. When you add power, gamma and gamma cancelled, and you are left with what? P final V final minus. Same thing here. Gamma, gamma cancel, and you get P initial V initial divided by 1 minus gamma divided by this 1 minus gamma. That's your work done in an adiabatic process. Again, an important result for you to remember. Now, what is this? P final, V final minus P initial, V initial. Whatever type of process you consider, you take, it has to follow PV equals to nRT always. PV equals to nRT. Ideal gas equation, considering each and every system is ideal for us, which it is. So PV is what? nRT. What is P? P final, V final. What is P final, V final? What is P final, V final? This P final, V final is coming nRT final. If you use the equation PV equals to nRT, it implies that P final V final is what? nRT final. At the same time, it gives you P initial V initial as nRT initial. So, put these values in this equation. P final V final, that is nRT final, minus P initial V initial, which is nRT initial, and you got what? nRT final minus T initial divided by 1 minus gamma. Work done in an adiabatic process in terms of pressure and volume, in terms of temperature. And all these are statements which now you need to remember. What is work done in an isobaric process? nR T final minus T initial. nR T final minus T initial in isobaric. What is work done in an adiabatic process? Same, NR T final minus T initial, but divide that number with 1 minus gamma. As a trick, you can use it. Work done in an isobaric process divided by 1 minus gamma is work done in an is work done in an adiabatic process. Note down everything. Now suppose I ask you that what happens in an adiabatic process if volume is increased, then what happens to temperature? It increases or decreases? And you need to answer this part with the help of everything written on the board and which I have taught you so far in thermodynamics. My question is that in an adiabatic process, if your volume is increasing, if volume of the system, if volume is increasing, then what happens with temperature? It increases or decreases. And you need to answer this part with the help of this part, and something which I told you about work. And pause the video, think about it, and then come back and see how you can answer it. If you say that volume is increasing, if volume is increasing, immediately you know that work is positive. When volume increases, piston is going up, force and displacement, they are in the same direction, and therefore your work is what? Positive. So if work is positive, then this part is also what? A positive number. NR T final minus T initial upon 1 minus gamma. This is a positive number. But look at the denominator. I told you that for an adiabatic process, gamma is always greater than 1. If gamma is always greater than 1, then somebody using this format will say that denominator is negative. If denominator is negative, then what should be the numerator so that whole thing comes what? Positive. If you use this or you use this, your work, if volume is increasing, should be what? Positive. That means denominator is negative, make the numerator also negative, and then your work will be what? Positive. How do you make numerator negative? Your T final should be less than what? T initial. That means with the help of this much information, you found out that T must decrease. For an adiabatic process, if volume increases, then temperature must always decrease. You will get so many one-line statements in this chapter, and that's a good thing. You can always make a chart and remember the chart, remember all these one-liners, and you can use them in any examination you wish. Now, before we finish the work part, it's not the whole thing is not restricted to isobaric, isothermal, isochoric, adiabatic, and all. Let's say somebody gave you a fifth example like this. They gave you that pressure is 2V plus 3V square, something like this. They made a random equation for you, an artificial equation for you. They haven't told us that it's an isothermal, isobaric, isochoric, or an adiabatic process. They just gave us that P is this, and then they told us that V initial is 1 and V final is 2. They gave us this information. The question is find out what. For any process, If it's not a standard process, which we have discussed so far, you don't have to worry anything. Your calculation part will start from this. What is W? Integration of dW. What is that? PdV. Can you integrate this? That's the only thing you need to ask. Yes, we can. Yes, we can. What is this? 2v plus 3v square. Write down this 2v plus 3v square multiplied by dv. Everybody can integrate this thing. This is like x dx. This is like x square dx, and therefore you can integrate it like this. This is giving you, let's use the direct integration, 2 v dv is v square by 2. So you got v square by 2. 2x dx, v square by 2. Then 3v square dv, x square dx. Its integration is coming v power plus 1, 2 plus 1, 3 divided by 3. 3v square divided by 3. Starting from lower limit, v initial, to final limit. This is 2 and 2 cancel, 3 and 3 cancel. This is your v square plus v cube. Limits 1 and 2. How do we use limits? Upper limit 2 square 4, 2 cube 8. Upper limit 2 square 4, 2 cube 8, 8 plus 4 12. Upper limit minus lower limit 1 1, 1 square 1, 1 cube 1, 1 plus 1 2. You got 12 minus 2, and your answer is coming what? 10. For any process, if you do not have the direct result, you can always proceed with what W is integration of dW, which is what P dV. Wrote down everything.